tree, an overview about them, and some quick examples on Python. So the problem with balancer tree is that depending on the order or resetting element in the tree shape can vary to different forms. Such in the base case, you can see in the right side we have a well-balanced tree, but also we have some worst cases, such as inserting elements in the order where the tree will look like a linked list, which each node has only a right child, and this is not a good balanced tree. So to do a self-balancing balanced tree, we have some methods to do. We have AVL tree, split tree, P tree, and red and black tree. The use of them occurs by databases indexing. As you can see in the illustration, we have the dots, signs, and the dash. As you can see from the start, the root node goes to the A and T. T goes to the right. If you said last time, it is greater, then E is less. Then later on, we go to the numbers 5, 4, with the H node, 3, with the V node, F is empty, and the F2 and the empty U to the right side node, and so on, with the numbers 1, 6, 7, 8, 9, 0. Directories in Ntfs are indexed to make finding a specific entry to make them even faster to find. A bit-tree index can be used for column comparison in expressions that use equal, greater than, greater or equal, less and lesser or equal, or between operators. The index also can be used for like comparison if the argument to like is the constant string that does not start with a wildcard character. For example, the following select statements use indexes. This is from the SQL language from databases. If you can see, we can select the star sign, which means select all from the table where key column is like Patrick. As you can see for the percentage sign. Don't forget in SQL we use the semicolons in the end, so it means that this is over for the first statement. Then we use the second sign. As you can see, select all from table name where key column like pet with the percentage sign underline CK. So means that only rows. The first statement means only rows of Patrick less or equal to key column, and means the PATRCL are only considered now. In the second statement, only rows of pet less or equal key column PAU are considered, PAU are only considered now, as you can see from the second statement. But what happens with the red-black trees? The aim is to keep the tree balanced without affecting the complexity of the primitive operations. This is done by coloring each node in the tree with either red or black. It will preserve a set of properties that guarantee the deepest path in the tree is no longer than twice the shortest one. Every red-black tree with nodes has a height of less or equal to 2 log n of n plus 1. A red-black tree is a binary search tree with the following properties. As we know, every node is colored with either red or black. All leaf or nodes are colored with black. If a node child is missing, then we will assume that he is a null child. In that place, this null child is always colored black because we don't know it. Both children of a red node must be black nodes. It is a rule, important rule. Every path from a node to a descendant leaf has the same number of black nodes, not counting the n node. Of course, we call this the number, the black height of n, which is denoted by BH of n. As you can see from the illustration, the root node is black, the children of the root node 13 are red, and the children of them are black. As you can see from the empty sign, we have to, of course, don't forget that if there it is empty, we have to write there null. We should not leave that empty. We should incomplete that with a null sign. As you can see, the last element are all red. The children of the red elements are black and the root is black. Don't forget the rules and properties, because this is how we will continue with them. We use two tools to do balancing search tree. We use recoloring and rotation. Coloring of a null node is considered as black, as I said before. Rotation is a binary operation between a parent node and one of its children that swaps in order traversal of T. As you can see from the illustration, the sixth figure from the left side, you can see we have 5, 7, and 8 on the right side. As you can see, this is not a good sign. If you done the calculation, we get a 2, 1 minus 3. We give us 2 value, and we won't get an appropriate properties on the red black tree. So what we do, we have to rotate it now. As you can see from the, if you can see the circle where after 5 and 7, it has rotated. Now 7 becomes the root node. Yep, that's right. Yeah, you're correct. Okay. Shall we continue or? Okay. As you can see, 2 and 6, the 6 will, of course, the 6 will go to the left side now. Yeah, okay, okay, we got it. Thank you. Balanced tree insertion, which takes big O of log n, as shown before. It will fix any violations to red and black trees property that may occur after applying the first step. This step is big O of log n. Also, as we start by fixing the newly inserted node, continuing up along the path to the root node and fixing nodes along the path. Fixing node is done in constant time and involves recoloring some nodes and doing some rotations. As you can see from the illustration, the root is black, but as you can see, the 14 is black. Why? Because we have done a rotation there. After insertion of the fourth node, we have done some fixes there. As you can see, yes, correct. 2, 1, 7, 5, 8, and 4. 4, which is a new element now, becoming red. Yes, correct. As you can see on the right side, this is fixed now. All the root is black, the children of root are red, the children of the red now are black, and the children of black now are red. And this is well balanced now, and it completes all the properties of red and black insertion. We perform standard BST or balanced tree insertion and make the color of newly inserted node as red. If X is root, we will have to change the color of X as black height of complete tree increased by 1. We have to do the following if the color of X's parent is not black or X is not the root. We have some cases now. If X uncle is red, grandparent must have been black. We have to change the color of parent and uncle now as black. Color of grandparent as red. We have to change X with the X's grandparent. Now we have to repeat the second and third step until we have a well-balanced tree with the numbers from -1, 0, and 1 now. Now we have to do the following if color of X parent is not black or X is not the root. We have another case now. If X angle is black, then there can be 4 configurations for X. X parents P and X grandparents with the G variable. We have the left case, if the P is left child of G and X is the left child of P. We have left right case, if the P is left child of G and X is right child of P. We have the right case, which means there is the mirror of case A, is the opposite of the P will be the right child of G and X will be the right child of P. So you can see the illustration, the uncle black and left case. You can see G, P, and X. 3 minus 1 will give us 2, so don't have a well balanced tree, so now we have to do some recoloring or rotation. As you can see, we have rotated the G and swapped the colors of G and P. Yes. X now is the current node, P is the parent of all of them, the U is uncle, and G is the grandparent. Yeah, of course, don't forget we have the right-left case, where the P is the right child of G and X is the left child of P. We have another case where uncle is black and we have to use the left-right case. We have rotated on the left side the P. We have to apply the left case method. And now the X is current node, P is parent, U is uncle, and G is grandparent. But as you can see now, T1, T2, T3, T4, T5, T5 are subtrees of all of them nodes now. Which means they are null, but we can complete it with the values, whatever values the user has to put in. Or if they are empty, we have to include them on the null side. Yes, we have to insert 10, 20, 30, and 15 in an empty tree. First of all, we insert 10, case tree, and now the X is root. Insert 20, which is greater than 10, go to the right side. Insert 30 to the right side. And now we have a problem. So you can see 3 on the right side, which means we have the linked list. We don't want that. What we do? We do the right case. 30 will replace 20, 20 will replace 10, and now 20 is the root case now. 20 will be in the middle, 10 will go to the left because it's less, and 30 will go to the right because it's greater. And if you do some coloring now, as you can see, the new elements were red, but now 20 becomes a node and is black, and 10 and 30 becomes red because they're the new elements, the new nodes, and we don't want a root node red. The null is considered as black, as you can see. 20, 10, 13, we put 15 now. We have the second case A, 20 the root, 10 and 30 with the black color, and 15 of the 10th node with the red color. We have the third case, and now the X is the root. As you can see, 20, 10, and 30 are black, and the new element 15 will be red. As you can see from some illustration, we need to insert 2. 2 is a node, we need to insert 1. 1 will go to the left. We have to insert 4. 4 will go to the right. We want to insert 5. 5 will go to the right. But now we have a problem, so let's analyze it. We put G, P, and X, case 0. Now we have to put 9 now. 9 goes to the right of 2, the right of 4, the right of 5. Now the 9 will be the red color. Now we have to recolor it and rotate because we have a problem now. As you can see, you have the color of 4 and 9 with red. And now we have to rotate the 5 will become the node, and the root node of 4 F9. 4 will go to the left side, and 9 go to the right side. Don't forget the variables, we put them in the fourth step, G, P, and X. If you want to insert 3, 3 is greater than 2, go to the right, is less than 5, left, less than 4, left. Now we have the first case. If we have to insert 6, 6 greater than 2 to the right, greater than 5 to the right, less than 9 to the left. And we found 6 with a new element which will be colored in the red. We have to insert 7. 7 is greater than 2, greater than 5, less than 9, but greater than 7. And now we have to recolor it because we have 6 and 7 with the same color red. So what we do? We have to recolor 6 now, and now 6, 5, and 9 will become the red, and 7 will be black. The second step is to rotate X about the P sign. Yes. So the 7 will become the new node, the root node of 6 and 9. 6 go to the left and 9 go to the right. Don't forget about coloring, it is important. This is the main idea about coloring. And 5, as you can see, before the last step, 2 is the main node, the root node. On the left side we have only 1, on the right side we have 5, on the left side of 5 we have 4, on the left of 4 we have 3, so we stop there. But in the left side of 9 we have 7 on the left and 7 on the 6, which we have a problem because as you can see there is a linked list now, and we don't want that. As I said before, 7 will become the root node of 6 and 9. So, yes, it becomes now. As you can see, we have a new cool node that doesn't make any trouble or problem, and the user now will not have any problem finding it or will not have any error of it. So it will be really effective for the user and for the program to flow easily. While AVL3 is a self-balancing binary search tree BST where the difference between heights of left and right subtrees cannot be more than 1 for all nodes. It calculates the balances of factor for every node if balance of factor is greater than 1 or less or equal to -1. As I said before, this is the range where we go 1 or -1. But of course we take only the absolute value of it, but don't forget 1, 0, -1. This is all where we go. If you go greater than 1 or less than -1, the node now becomes unbalanced. The AVL trees are more balanced compared to the red-black trees, of course, but they have some problems with rotations during insertion and deletion of them. So if our application involves many frequent insertions and deletions, then red-black trees should be preferred. As you can see, we have some example rotations. This is done in Python. Yes, as I can see from my subscripts, it's done in Python. We have T1, T2, T3, and T4 become the subtrees. Z is the main node, Y on the left. Do you think Y is greater than Z or less than Z? Of course, it is less than Z because it is on the right side. But okay, let's go. Y, we have less than X, become the right. T3 is greater, comes to the right. Go to the X. We have T1 on the left side, less. And T2 on the right side, right. But we have a problem. So see, we have like a linked list there. Z, Y, X, and T1, and we don't want that in our binary search tree, but well-balanced binary search tree. So we have to right rotate the Z. So now the Y node becomes the root. If you right rotate the Z, the Y becomes the root node, X becomes the left side because it's less, Z to the right side because it's greater, and now T1, T2 is on the X, T3 and T4 is in the zeta side node. So now we have a well-balanced search tree. It's really effective design. We have another example. If we would with the left rotate and right rotate, we have Z node, Y, T4, T1, X, T2 and T3. We have to left rotate the Y, but what happens if we do the left rotate? We still have a problem. So now we have to do the left right case. So if we did the left rotation, we would have zeta on the node, main node, root node, x and y and t1 on the left side. On the right side of z, we will have t4. On the right side of x, we have t3, and the right side of y, we have t2. If you do the right rotation of zeta, you would have x now as the main node, y is less on the left, and zeta which is greater on the right. And t1, t2 would be on the y, t1 is less, t2 is greater than y. Zeta will have t3 and t4, t3 on the left is less, t4 is on the right because it's greater than zeta. As you can see from rotations, some values there. We have only -1 there. Look, if there is empty on the node, we put the 0. In the first case, we have -2 and -1. Which, okay, this don't have any problem, but if you put any new value now, we have a problem because it become -2, and we don't have the range of -2. If it become greater than 1 and less than -1, we don't have a well-balanced search tree. It becomes unwell-balanced search tree. As you can see in the second case, we have that search tree. We have to insert 3. Of course, there is a huge problem. If you can see from your eyes, if you become more experienced with these problems, you can definitely see where the problem is. There is kind of like a linked list there, and we don't want that right there, because if you can put in the program now, Python will really detect it and become like an error, like a write back error, track back error, something like that. I don't remember well now. And the user will be really confused with that error, because if you search for example 16, and the program will go to the left side, 10, 11, now we come with the 4, with 8, with 5, while the 3 will always be complicated with our numbers. And if the user, even worse, search for the number that is not on our table, the program of our program would be completely destroyed. Now we have to do the right rotation with the node 10 as pivot. Now we can see the values. Now we have -1, 0, -1. This is on our range, and we want that. We have 13 with the root node, 5 on the left. As you know, left less, right is greater than the node. 4 to the left, 3 to the left. On the right side we have 5, we have 10. On the left of 10 we have 8. On the left of 10 we have 11. As you can see, 3, 8 and 11 have 0 values, 0 weights, because they don't have any nodes under them. 4 is -1 because 2 -1 on the left means that 1 -0 became now -1. 0 -1, yeah. -1. Don't worry, we won't take the absolute value of -1. So the new generation takes the absolute value, but there is still a sec. The program doesn't care. You always take the absolute value, which means the positive side. 5 is 0 now because 2 - 2 is 0. And now on the 13 node is really cool because 3 minus 2 will give us -1, and it is on our range. As you can see, we did the right rotation with node 10 as a pivot now. Pivot is slightly like a leading coefficient. As you can see, 10 is below 5 and greater than 5. It is like a pivot node. Of course, we have B-tree. We call it the fat tree. The main idea of using B-tree is to reduce the number of disk accesses. The height of B-tree is kept low by putting maximum possible keys in a B-tree node. Since H is low for B-tree, total disk accesses for most of the operation are reduced significantly compared to balanced binary search tree like AVL tree, red bank tree, etc. You have some properties of B-tree. All leaves are at the same level. A B-tree is defined by the term minimum degree T. The values of T depends upon our disk block size. Every node except the root must contain at least T-1 keys. Roots may contain minimum 1 key. All nodes, including roots, may contain at most 2 times T-1 keys. All keys of nodes are stored in increasing order, which are between 2 keys. Key 1 and key 2 contain all keys in a range of key 1 and key 2. As you can see from our illustration, we have 3, 30 and 60. We have 1, 2, 4, 5, 6, 40 and 50 and 70, 18, 82, 84, 86. These are all combinations of them. But B-tree grows up, unlike binary search trees, balanced search trees, which are grow down. Functionality of split child method: 150, 100, 200 will split in 55, 70, 80, 85, and 90. Now we'll call some other numbers like T1, T2, T3, T4, T5, T6, the values, but don't forget, we use the 2T-1 as a key and T-1 for the nodes. This is a method we have done with functionality of split child method: 150, 80, 100, 200. Y is 50 and 70, zeta is 85 and 90. Now on the Y side we have T1, T2, T3. On the zeta side we have T4, T5 and T6. We have done an example now. Yes. With a minimum degree of T is 3 and a sequence of integers 10, 20, 30, 40, 50, 60, 70, 80 and 90 in an initially empty B-tree. We have to insert 10 now, and we have to insert 20, 30, 40 and 50. If you insert 30, it will become now independent. 30 will be the main, also the root, as you would call it, no problem. On the Y side we have 10 and 20, zeta side we have 40 and 50, or another example, 30, 10 and 20, 40, 50, 60, if you insert 60. We have to insert 70 and 80. On the Y side would be 10 and 20, zeta side would be 40, 50, 60, 70 and 80. But if we would insert 90 now, as you can see, become more balanced now. 30 and 60 will be on the X, also the root, 10 and 20 on the Y, 40 and 50 to the zeta, 17 to the 80 to the theta. So this is the end. Thank you for sticking with me. I know this was like complicated topic, but don't worry, take another look and please write down in the comments what you don't understand and I will explain them step by step. Don't worry. Thank you for checking me out, and don't forget to hit the subscribe button and like that video, and we're gonna go with another topic which is really important.